Here's a simple three-state state machine. State idle, state wait for max recrossing, and state. There's transitions between the states. If we see that Ex is greater than max, we perform some piece of code on the transition, and then we enter into the state wait for max recrossing. Likewise, the other direction, if Ex is less than min, and then when we're sitting in one of the wait for recrossing states, it waits until X is less than max. The E stuff is just an environment variable that encapsulates the X max and so on. I convert this diagram to a simple textual intermediate code, a language that I'm calling .sm. This is out.sm in this case. And the machine is set up in the make to call it looper, and it has the three states: state idle, state wait for max recrossing. Wait for max recrossing is over here, and state wait for min recrossing, which is over here. And in each of the states, there's three parts. There's an enter, there's a step function, and there's an exit. And in this simple example, the entry and the exit really don't do very much. Every time the state machine is called, it's given an event to try to step itself, and if X is greater than max, which is this one over here, it performs that piece of code, transition code, E.reverse. And likewise, for the other case, it does that. And otherwise, and when neither of these cases is true, it just falls through, remains in its current state, and continues on. So every time it gets hit with an event, it checks these states. If one of these nexts fires, it performs this wait for max recrossing. So that's this transition test. So this is the guard here for the transition. And if the guard evaluates to true, then we fire this piece of code, and then we change to that state. And that's what this line here says. And likewise for the rest. Then we take that same code, convert it to Python, and we see the same, the pattern: enter idle, step idle, and exit idle. And here we see the transition tests, the guard. That's the guard. And if the guard fires, then we exit the current state. We perform the piece of code here. This is the piece of code. And then we enter into the next state down here. We can write this differently in Python. This is the way I've written it. It was very simple to do. Again, this is just a tool for programming, and I don't really care if the code is maximally optimal or not, just as long as it's true to the diagram. On reviewing this code, I see that there are two transitions possible out of this idle state. And the way these guards are written, both will never fire at the same time, although I would prefer that only one transition ever fires. So if this one fires, this transition won't be visited. There's several ways to write that code. We could just make these all into elifs and put a null if at the beginning. If false pass. Another way would be to insert a return statement here and here. And that's what I'm going to do. The code emitter is easy to change. I only need to look at the insides of this part. This part uses the T to T tool, which takes a grammar and a set of rewrite rules, and it's the rewrite rules that we need to change. So we go into smmetapy.rwr. We find the next rule, and then we just added a return at the end. And if we run that, and look at the code, nuclear.py, we see that the returns have been inserted. As we can see, the diagram itself is much more descriptive of what we want to happen. This Python code down here does the job, but to my eyes, it doesn't actually give me the same information that this diagram does. I've included a more complicated diagram in the README. This is experimental code. I'm trying to use the state machine drawings to do collision detector in the PBP-Pong project. This is my first attempt, and it hasn't been debugged yet.